So let's see. So there is this assertion failure. I can either walk you through the idea, or we can try to debug this together, or both.
I'm up for either.
All right, why don't we go through the high level idea, and then proceed to maybe debugging will give us a nice way to explore the code in a purposeful fashion. But right, so the idea. So actually what I'm trying to decide, I guess I'll walk through what's on the branch exactly, and then we'll go from there. I have a different branch where I refactored the code to isolate out the stack logic, and I think it's easier to follow, but it might be confusing if I started with that, so I won't. What do I want? I want select mod. So this is annoying. Do you have this problem? Maybe I should figure out how. There's got to be a way to tell it like, I'm not interested in LVM. Please put them at the bottom of the list.
Yeah, I have that problem sometimes. Yeah, I don't know.
It turns out like every unique substring appears in LVM somewhere, and often many times.
Yeah, doesn't surprise me.
Also, we do use a lot of the same words. Like
also
both compilers. Yeah. Anyway, okay. So, right. So trait evaluation is a fairly straightforward process in which we do basically a sort of depth first search down to try to decide if a trait might be implemented. It's not entirely clear why it exists in addition to the other mode of evaluating traits, except that Niko didn't know what he was doing when he first implemented this code, and it grew into this structure. But that's all right. It has.
Wait, so what do you mean by different than the other way of evaluating traits?
So there's two ways that the compiler evaluates traits. They're connected and interrelated and not entirely separable. Mm-hmm. There's the fulfillment context and the evaluation logic.
Okay.
And the fulfillment context sort of does I'll call it a breadth first search. That's not really true. Mm-hmm. That's actually maybe just kind of misleading, but it basically keeps a queue of work to do. And if you have to prove that one impl or that T implements some trait, some type T implements some trait, it will figure out which impl you're using and take the where clauses from that impl and add them to that queue, right? So that's like one distinct step. That's trait selection, or I call that trait selection.
Right.
Is picking which impl you're going to use, but it does that without necessarily knowing that the where clauses are satisfied. Mm-hmm. The problem is, and this is where the two systems arose, that was the first inspiration for how it should work. And in old Rust, when that was implemented, like we didn't really have where clauses for the most part. So it wasn't that complicated to do. And we had where clauses, I guess, but we didn't have, our coherence rules were much simpler, such that like basically at most one impl would unify. So that was fairly straightforward. And then when we tried to extend it to allow for things like, I have an impl for all things that are clone and an impl for something that's not clone, we had this problem that we couldn't pick in the same way. And so we added trait evaluation, which basically tries to figure out, is this type, it does it instead of like unrolling and pushing things onto the queue, it tries to go down all the way and figure out, do all the where clauses, are they all satisfied all the way down? Can I just fully prove this out? And it's not always, it's sort of a try value, right? Like it comes back with an evaluation result, which is either like yes or probably, but there's some region relationships I couldn't verify because I don't know how to do that. Or I couldn't tell one way or the other, or some other variation of I couldn't tell one way or the other, or no, it does not. There's no such impl that could potentially apply, and recur is like another thing. And so and it's for cycles and stuff. And so, right, so the code is fairly straightforward, like proving the trait predicate. So we have this stack. I guess that's the other thing. We keep a stack of the context in which we had to prove something. When we're doing at the fulfillment context level, that stack is always empty. Like everything the fulfillment context starts to work on is the top of the root of the stack. It's the first thing is finding the impl that applies for a given thing. But when we're doing the evaluation, we can go deeper in, where we're processing the where clause and then the where clauses of the where clause and so forth. And this is the stack type. It is, well, actually, this is an iterator. This is the stack type. And it's just a linked list. So it has a reference to the previous element on the stack. And then this is the top of the stack. It's a linked list.
Could you maybe increase your font size like 1 or 2?
Yeah, good point. Maybe.
Control plus, I think.
Zoom
Maybe.
in. Does that work? Okay.
There we go.
Is that better?
Yes, thank you.
So yeah, this is the top of the stack. We push things on by calling, well, by building another one of these structs with a reference to the previous top of the stack. So it actually walks up the real program stack as well. And jumping
Like
back
putting
out.
my chalk hat on and like thinking about how this is similar and different.
Yeah, it's similar to the recursive solver, you know, but different in certain respects that I'm about to go into. So, but this PR is, among other things, moving the evaluation model closer and closer to how the recursive solver works. And like to shift gears to chalk ever so slightly, I haven't fully mapped this out in my head yet, but I do think one way to get chalk into RustC, as we were sort of discussing, is to tweak how RustC works so that it uses the evaluation more and more, which we've also been moving from time to time for various other reasons. And then like the more we're able to lean on this instead of the fulfillment model, the closer we're getting to how chalk's going to interact. And that could be useful. And then we can also bring like lessons from chalk to make this evaluation system better because it has certain limitations. So, right, evaluation starts here at this evaluate trait predicate recursively, which gets called by some other, it doesn't really start here, but the interesting stuff starts here. And first thing it does is push. So here's the old stack. We're going to push onto the stack, which means make a new struct. If you go through, you'll see it just instantiates one of those instances. We track the depth, and this will be important. We track this depth first number. That's familiar to you from chalk, I'm sure. It's just a counter that increments. The difference between them is when things get popped off the stack, the depth goes down, but the depth first number never changes, or it just keeps going. It's monotonic, which is useful. So then we do some, I'm going to ignore this caching, although it's going to turn out to be pretty important. But for now, let's ignore it because the whole bug is around caching. So it will be important. But we look for a cycle. That will also become relevant, but let's ignore it for the moment. And then we do this thing, evaluate stack. So this is what does the actual work. This is like, okay, I have a stack. I want to check if the thing on the top of the stack is true, false, whatever. True, false, or unknown. And I've already looked for cycles and checked the cache and done all that stuff. This is do the actual work. So what does it do? Ignore this stuff. This has to do with coherence. And it's basically makes us fail to, I don't know, I forget what this does. Who cares? Something with coherence and like making us not try to prove things that would be bad for coherence. This is the interesting part. So here we call candidate from obligation. What that does is it finds, so a candidate in the parlance of this code is basically a way to prove that a trait holds. And so this is the this is the point where, or this is one of the points where we break from chalk and from a traditional, like a more capable theorem prover, because really what we should probably get back here is a vector of candidates. There can be many ways to prove that the trait holds, and it sort of doesn't matter which one we do, as long as we have one. However, we force ourselves to return one with some horrible heuristics that you're vaguely familiar with and that we will not go into here because they're not relevant. And so we get back one of these options. Either we get back a selection candidate. That means we found what we think of as the right way to go. We found the impl. Let's take the easy case. There's exactly one impl that unifies and might apply. This will information about that impl will be in C. If we get back none, it means there were ways to go, but we couldn't figure out which one. There were too many impls that might have applied and we couldn't narrow it down. That could happen if there's inference variables, for example. Like if we're trying to prove that $T implements a trait, that could be any impl. So long as there's at least two impls, we're stuck. Or where clauses, stuff like that. Overflow is overflow, and otherwise, if we get back error here, it means there was no impl that might apply. There was no candidate. We couldn't find one.
Is it just me, or would like an enum here make more sense than a nested option of result?
It's not just you. Yeah, I don't know. We might use question mark in it. Yeah, there are some things that could be improved. For one thing, I noticed as we're walking through here that also like error is used somewhat differently, right? Like for evaluation, you can have an OK with evaluated to error, and an error is just used for overflow. But for candidate, error means no candidates, which is a little confusing. Yeah, you're not wrong. So nonetheless, the happy path is we found a candidate. We jump into evaluate candidate. What does evaluate candidate do? Evaluation probe just prevents inference variable side effects from leaking outside. So what confirm candidate does is it takes like we figured out which impl applies. Confirm candidate will unify all the types from the impl with the types of the thing we're trying to prove. So as an example, if we had an impl, if we were trying to prove like option of $T is foo, and there's exactly one impl of foo that was like impl foo for option of I32, then this confirm candidate would unify $T with I32. More commonly, it goes the other way, that we have a type that we know and an inference variable which arises out of the impl. Like we replace T with a fresh inference variable as part of the confirmation. And then we unify them, and so T becomes unified with I32. But then we get back from this a list of, well, we get back what's called an impl source, which is kind of related to the candidate. It's sort of the information, but the main thing that's in there that we're interested in is this nested obligations, which is basically the where clauses. And so then we're going to go recursively evaluate them and say like, okay, well, the impl applied, we were able to unify the impl, everything succeeded. Now let's check if the where clauses apply. And that's the whole recursive concept. So far, so good.
So far, so good.
All right, we're going to pop back up. This is actually the root of evaluation. Evaluate predicate. Before I showed you like evaluate trait predicate, which is called here. But that's just one case because there's different kinds of predicates. But most of the others are not that interesting. Like if, for example, we're forced to prove some region relationship, we can just say, yeah, that seems good. It's good as far as we know. And there's like some other stuff here, but it sort of bottoms out to, this is the main case. Okay. So jumping back, I want to talk about the caching and the cycles. Let's talk about cycles first. So what do we do? Where did I? That's the other problem I have with VS Code is the back is like it's good because it has like every place my cursor landed, but sometimes it takes me a while to find the one I want.
I didn't
Okay.
even know there was a back option, so
Oh yeah, I don't know how you live without that. Control
dangerously.
dash on Mac, but it changes on other platforms.
Okay.
So check evaluation cache, and that's not what we're talking about. We're talking about check evaluation cycle. So we have the stack, and the main reason we actually have the stack is so that we can, sorry, just having a little thought. Oh, right, I remember now. So that we can detect cycles. And what do? We iterate, it's very simple. We basically iterate up the stack, looking for something where we have the same thing we have to prove, or the environment is the same and the thing we're trying to prove is the same. Fresh trait ref, that's an old version of canonicalization where inference variables get replaced with like an integer that is ordered by their appearance. It's basically the same as canonicalization. We just have two ways to do it that are similar but different. Because this one was done first.
That's great.
Yes, isn't it? Right. So we iterate over the stack. We look and see if any of them are there. If there is one, we extract its depth, and we say, okay, we found a cycle. And this is where the assertion is failing, as an aside, or one of the places it might be failing. And then we call update reach depth. So what is that? What happens is for everything on the stack, we are tracking what is the up and down are always kind of problematic. What's the oldest thing on the stack that you depended on, right? So if there's no cycle, then it's just going to be yourself, basically. So I depend on, in order to prove that T implemented foo, I had to prove that T implemented foo. That seems fine. But if you end up with a cycle, like usually with auto traits, here's an example right here. Like you're proving foo of T is send, that requires proving bar of T is send, and maybe bar has a foo inside of it. So then I have to prove the foo of T is send again. Then I would update the reached depth of bar of T to be equal to the depth of the foo of T. So if this was 0 and that was 1, and that's 2, but it doesn't ever get pushed, then this would have a reach depth of 0. And that's useful because that tells me that especially for the co-inductive cases, bar of send is true so long as the things that were higher on the stack up to the reached depth are also true. It's kind of conditionally true, or provisionally true. Right, so that's what the checking cycle basically does. It tracks how high did you go. It checks if it's a co-inductive, if everything in that cycle is co-inductive, in which case it's okay, but we updated the depth. Otherwise, it does this evaluated to recur, which either way, we're gonna stop, right? So either we reached a cycle, which will be treated as a kind of error, or we are considering it okay, but we had to mark things on the stack to indicate that that was like a provisional okay. And so that's where we come to this caching business. So then, zooming out now, if we were doing this case of foo bar foo, when we're processing foo the first time, there's no cycle. We go into the evaluate stack. We come in here for bar, no cycle. We go into evaluate stack. Now we come back for foo. We hit a cycle. We're going to mark bar as having reached an earlier depth and return. And then we're going to come back, and now we're still at the point where we're proving bar. So we basically will have proved, evaluate stack will have returned okay because that cycle was checked and returned okay. So we now think, okay, bar is proven. And ignore this for a second. We're going to look here at what depth did you reach? And the question is, if it is, if you never depended on anything above you in the stack or older than you, I should really stick to older, anything older than you on the stack, then you're kind of self-complete, right? So you're done. But in our case, where we're processing bar depended on foo, which was older in the stack. And
Mhm.
therefore, we can't consider that to be completely evaluated. So we use this thing called a provisional cache. And the idea is that essentially attached to the stack itself, we have a cache. We have several caches at different layers, depending on how true that thing is. But for our purpose, for this particular bug, we can just think about two caches. There's like the global cache for stuff that we really know is true.
Mhm.
And then there's the provisional cache, which is attached to our stack, which is saying, we proved this to be true, but it was subject to something that's still on the stack.
Okay.
So it's true unless that thing turns out to be false. And we'll track, we pass in what was our depth first number,
Mhm.
what was the depth that we're dependent on, and what was the result. And now when you come back, if, for example, you had foo of t had to prove bar of t, then bar of t would be added as a provisional cache hit because of the cycle. But now suppose that then foo has to prove baz, and baz has to prove bar as well. Okay. Now we have another cycle because, or if we went and recursively processed bar again, if we ignore the caching, we would get a cycle just like before, where bar would depend on foo, and it would mark bar would depend on foo. Let me put the comments because it's clear in there's a visualization in my brain, but it may not be in yours. I'm going to write out the
I
whole
think I
process.
can do it, but for the people who are watching the recording, it would definitely be helpful.
That's what I'm imagining. So we basically had, let's replay it. We started out with foo, we pushed bar onto the stack. We pushed foo, we got a cycle, right? Then we marked bar as reached depth equals 0. In processing that cycle, and we marked this as okay. Then here, we would consider this okay, because all of its children are okay. But then suppose that for foo, let's add like depends on bar baz. So in order to prove foo was true, we had to prove bar and baz. So we started by proving bar, which we have done, and then we went to prove baz. Baz, let's say, depends on bar. Okay, so then what we're going to do, I'm just going to ignore caching for a second. Pretend we did everything with no caches at all. Then we would go to bar, and we would say, okay, well, bar depends on foo, just like before. We'll push foo. Here's a cycle. You could think of this as a cycle. Reached depth equals 0. Okay, you can sort of see I'm evolving a weird notation here. This would be the same. We found a cycle. The depth of the thing was 0, so we reached depth 0. We consider ourselves okay. This guy is going to say, okay, well, my reach depth is 0 because I have a child that reached. So the way this works in Chalk, and the way I would like to think of it, is that your result is not just okay or error, but your result comes with the depth that you reached,
Right.
or something like that. That's not the way we've implemented it here, because it was stapled on to an older system that didn't understand this stuff. So the depth is like stored in the stack as a kind of side mutation thing. And only the okay is passed back. We should probably refactor that at some point. But what that means is the way this is actually working is that at each point we are initializing the reach depth. So it starts out with the depth of the current node, right?
Mhm.
And then when we find the cycle before we've actually returned, we're going to go back here and update these to be equal to the minimum of their previous value and the cycle we just encountered.
Okay.
And then we're going to return. And then here we're going to return. And here, let's say there's no more dependencies, so we return. And now we get up to here, and we can return. Our reach depth here started out as 0, and it never changed because nobody was able to reach past the top of the stack, or the bottom of the stack, rather, the root of the stack. And that's fine. That's how this would work with no caching. So what do we do now? What do we do instead? Or what do we do? The problem is we repeated some effort here. And that's one problem. Another problem is we would like to cache all these results so that if anybody in another function should try to prove the same thing, they don't have to do the work again either. We would like to do both those things. So we'd like to save ourselves some work while we're doing it and save future callers some work too. And those are a little bit different. So the way that we do this is, we'll first just talk about saving ourselves work. When we see a cycle, or rather, let's first talk about saving other people work, I guess. So there's a global cache of things that we've proven true, right? And when we get an okay result, we like to put things in that cache as soon as we can, because then everybody else can make use of them. The problem is we can't put these internal nodes, like we can't put this foo in there, for example. We did find that it's okay, but that was part of this big cycle thing, and it's only okay if all the other parts of the cycle turn out to be okay. The same with bar, as it happens, because its reached depth was older than itself, it's a provisionally okay result. It can't be cached globally yet, because maybe it will turn out that Baz is not true, and we don't know that yet. And the same with Baz. Well, with Baz, it turns out it's the last thing we have to prove, so it would be okay, but we didn't figure that out yet either. So what we do is we have this provisional cache. And if we kind of replay, when we got to the point where we proved bar to be true, not for cycles, we don't do it there, although I mean, you could, I guess. Anyway, doesn't matter. Instead of searching the stack, if you wanted, you could seed the provisional cache. Now that I think about it, it'd probably be more efficient. But in any case, what we do instead is when we see bar and we see that it's okay, but we see that the depth is older than ourselves, that's this path, we insert into the provisional cache this entry. So we'll say, okay, bar is okay with a reached depth of 0. And let me just walk into the provisional cache for a second. What does that look like? Cache is very simple. It's a, well, that's interesting. Well, anyway, here's a bit of break from Chalk. Also, the key is the thing we're trying to prove. We don't store the environment because we assume the entire stack has a single environment. That's stupid. We should fix that. Small thing. And the value is this provisional evaluation. So what was the result? What was the depth first number from which I tried to prove it? That's useful later. And what depth did it wind up depending on? What was the oldest thing it depended on? Okay, so we're going to insert that in the cache. And now when Baz comes and wants to prove bar, it's going to find it in the cache here. Get provisional. Get provisional is going to, here, just do a hash map lookup. It returns a provisional evaluation. And the main thing is we can return the result, but we have to act as if we reached the depth of that cached value, because effectively we're replaying this search. We're just short circuiting it to the result. So if we redo this, what would happen with the cache? Just to like play it through and not require you to hold state in your mind. We would start here. We would say this is okay. We would cache provisionally. We would go to prove bar Baz. We would say, okay, this has a reach depth of 1 to start. We know that it depends on bar. We would come to bar, we would say cache hit. It's okay, or it has a reach depth of 0. That would cause us to go back up and tweak this to 0. We would then return okay. This would return okay, and then this would get cached too, because it is also a okay result that depends on something older in the stack. Okay, and then we would get up to foo, and at that point, foo now has its okay result. But unlike these other sub results, the reach depth of foo is not older than itself. So we've actually found the start of the cycle, which happens to be the root node, but that's not important. And so that means that not only is foo okay, but we know that these provisional cache results are also true. And so now that's this case. Okay, the reached depth is no older than our depth. That's what that's saying. It's greater than or equal to, so it's younger than or equal to. It actually will
I was like, that's backwards to how I think, but no, that's right.
Yeah, that's right. I think if I were to write this again, I would write if stack that depth is less than or equal to, but
yeah,
I find greater than or equal to be a very, my mind wants small things on the left. But anyway, that's how it was written. I don't know. So by me, I'm sure, but it made sense at the time. So the what does it do? Right, insert evaluation cache. That's the global cache. Unlike before, we called insert provisional on this cache associated with the stack. We're now calling insert evaluation cache on the whole inference context, well, the selection context. And what that's going to do, ignore this for a second. That's going to go, and inside the inference context, it's going to insert, keyed by the parameter environment and the trait this time, which is correct, the depth node and the result. And then we actually have this global cache too. What's the difference? The evaluation cache is tied to things. Basically, if that looks like something that is just true for everyone, like U32 send or something, we'll use the big global cache. And if it has inference variables or others, or like generic parameters or something, we'll use the inference context cache. This probably doesn't, they sort of both need to exist, but not entirely. I like Chalk's version of this better, using canonicalization and stuff. And then this is the other part. On completion, what does that do? This is what I actually changed in this PR. So mostly, what this does is it goes through everything in the provisional cache that is covered by this cycle, basically, and goes and puts it in the global cache. Because now, like I said, bar and baz, we not only know that foo is true, we know that the things that were dependent on foo are also true. And here's what changed. In order to show what changed, I have to make a slightly more annoying example. And maybe to explain how this works better. So this example had only one cycle, but the actual example from the bug is more like A depends on B, depends on C. Well, we don't need to make it that complicated. A depends on B, which depends on A. So now we have a cycle. Depends on C, depends on D, depends on C. Now we have another cycle, and that's the key point. This cycle is sort of contained within this greater cycle, right? And I think in the actual example of the code, like A also depends on like an E that depends on C. This doesn't really matter, but that could happen. And so what we used to do in the old code was we kind of considered this all one big cycle. We would wind up, we had for the cache itself, a reached depth. That was the minimum of the reach depth of all of the provisional entries in the cache, rather than having a per entry value.
Mm-hmm.
And so we said everything in this cache becomes true at that depth. And that was okay. Like that sounds like an approximation, a less good version of what we do now. But it actually led to incorrect results because there's one little detail I didn't show you, which is this dot max. So we're not actually storing the result that was cached, this OK result. What we're storing when we go to the global result is, sorry, just having a thought. Is there a subtle weird bug here? I think it's okay. What we're storing is, I have to think about it though. What we're actually storing is the max of that and the result from the main cache. And there's this other little weird thing about failure. Let's ignore failure for a second and assume everything is true. The real problem here is there's two versions of true. There's OK and OK modulo regions. So things can be less true, but still true. Where we say, well, we had some region stuff to prove and we didn't evaluate that. And so what was happening in the bug is, let's say to prove E, this is OK modulo regions. Let's say it depended on C and it also depended on, this was the actual thing in SYN. Depends on some type outliving tick static, which actually we could just prove. It's kind of, because like this is like literally a struct. We don't need any fancy region logic to know that that's true, but that's a very special case. So we said, okay, well, this is OK modulo regions, which makes E OK modulo regions, which makes A OK modulo regions because A depends on all these things. And then the idea is, well, for example, take B. B depends on A. So B isn't really OK. B is only as true as A is true. So B is actually, even though we got an OK result when we just looked at B in isolation, that's because we were assuming A was OK modulo regions, when in fact, sorry, that's because we were assuming A was OK. But if we reran this result to a fixed point, and we started with A being OK modulo regions this time, instead of assuming A was OK, we would actually come back with OK modulo regions here. Make sense?
Yeah.
And so what we're doing is we're kind of cutting, instead of rerunning to a fixed point, which is probably what we should do, or is like the naive thing to do, we're just doing the dot max here because we know some stuff about our logic system, and we know that it doesn't do anything besides propagate truth up. It doesn't have negation in particular. And so, yeah. So that's what's actually happening. And that's all fine, except for this part, because we would do that same thing to the result of C, which was also OK. Whoa, what just happened? Okay. Somehow I hit something. And so that means we would, C and D were also OK, but if you look at those, even though they're sort of amongst, it's a sub, even though it's like in this, it's a different strongly connected component because from C you can't reach A. So actually C isn't dependent on A, and the fact that A is OK modulo regions doesn't affect our C result. It should just be OK. But because we didn't track that for each entry in the cache, we couldn't recognize that. And so we wound up caching OK modulo region. And that was okay because for the most part, that distinction doesn't really matter until in the incremental version, or for whatever reason, when we restarted and reran, we happened to compute C without starting from A, just starting from C. And in that case, we would get the proper result. And so we would get an assertion failure, recognizing that we actually got two different results without any change in the inputs. So that's the bug. And the fix is that now we store everything per depth. And that means when we get to C, the reached depth of C is just going to be itself. And so we're going to clear out everything. At that point, we haven't looked at E yet. Keep that in mind. So we're going to clear out everything with a higher depth first number than C in the provisional cache, but not things with lower depth first numbers. So when we get to C, let's say contents of provisional cache when we finish with C. We're going to have B is okay with a reach depth of 0. And we're going to have D is okay with a reach depth of 0, because in the course of proving C, we had to prove D. We haven't gotten to E yet, so that's not going to be in the cache. Oh, and I'm also going to add in the DFNs just for fun. This is going to have from DFN1. This is going to have from DFN2, which is the, or 3 rather, because this is DFN0, 1, 2, 3. And so we're going to look for everything with a higher DFN than C's DFN, which is 2. And oh, and this reach depth is not 0, it's actually 1. And we're going to move it to the global cache. And we're going to max it with the result of C. So we're going to move C and D into the global cache.
That should be 2, right? Not 1. 1 is B.
No, this is depth. That's confusing. There's no reason to use both DFN and depth, except that we do.
Oh, great.
That's one of the things I refactored in my branch. We only use DFN, which I found to be easier to think about.
Yeah, no, that's confusing.
DFN has the advantage of not being reused. So when you're grepping through logs and stuff, you don't get like weird results. But otherwise, I think you could use either one here because it's, but anyway, we use different ones and it's confusing, but that's what we do. So yeah, 1 at this point is C for the depth.
Right.
So yeah, so that's the fix. Everything else just works. I think I didn't really change anything else in this branch. The only problem is we're getting this assertion failure, which I don't understand. Let me just check what's on my schedule. Oh, right. Okay, that's all right. I have a phone call to make. Other than that, we're okay. It's one of those things where any business that doesn't open before I start working, it's very hard for me to deal with because my brain gets into rest and like it doesn't let go until like 7 p.m. and then most businesses are closed. So anyway, where were we? Right, the bug. So I don't know what the problem is. Let's take a look. It's an assertion failure. The problem is update reach depth. And maybe the assertion's just wrong for some reason. I don't think so. We're asserting that yeah, it's weird. Why is that? That does seem weird. We're asserting that no one ever tells us to update our depth to something below us or newer than us.
That makes sense, I think.
I think it does, right? Because if there's a cycle, then either we're the start of the cycle, so it should be equal to us, or it's older than us, or if it's newer than us, then it's not, doesn't affect us, so why do we care?
Right.
It's not actually harmful. Like, it may be that it's just getting called and it's not harmful, but it's weird. I'm wondering, yeah, so, oh, there's one other thing before we go on to this bug. I just want to mention. One thing that the logic does do today, I changed this in my branch and I think it's right, though I have to completely convince myself. If the result is not okay or okay modulo regions, it clears everything on the cache that comes after it. So in other words, going through our whole example here, if A had turned out to be an error, we would have cleared this provisional result and we would never move it to the global cache. So this dot max that's occurring here, I believe you could put an assert, and maybe I should, that result, this code should only ever execute in the case where the result we're maxing with is either okay or okay modulo regions, because otherwise the cache should have been cleared. I don't actually think that's necessary. I think it would be okay to, like, if the result was error, we could cache error because it's not true. And when we reevaluate it, we're going to get an error. But yeah,
So
I don't
what
know.
was your reasoning for discarding error?
I don't know. That's what I'm a little, I would like to go back and ask myself. I think I might have been a little nervous because it is certainly true that, well, basically the question is, I think it's similar to the dot max logic. Like, that's a shortcut that's making an assumption, which is that if we found that B is true if A is true, if we knew that A was false, we're assuming we could never prove B to be true, right? Which I think should be correct. Like, but if you had if you could imagine that the code might do something different, like say, try to evaluate A, and if I don't know, then I'll go down one path. But if I know it's an error, I'll go down another path. And like, in particular, the where clause winnowing and stuff, I wouldn't be totally shocked if there's some edge case where if we were to run this to a fixed point, it would do something different. So it makes me like mildly uncomfortable. But that code in general just makes me mildly uncomfortable. I think that's a good example why that code is bad. If we had negation, all this logic gets a little more complicated, which is why, well, we don't have negation in chalk either anymore, but like the old SLG solver, maybe before you started hacking on it, I can't remember.
I removed the negation.
You removed that logic, yeah. This is why it used to have two things: positive reached depth effectively and negative reached depth, because it basically, you will have to do somewhat different things. Where you're either saying B is true if A is true, or you're saying B is true if A is false, and that's different. But we don't have that because we don't have negation. Anyway, so let's look at this. What happened to my terminal? It's like gone. Okay, that's weird. Oh, there's like some anonymous terminals here or something. Very weird. Just gonna get rid of that. Something weird's going on. Let's try this instead. Rust backtrace. So I think what I found was, in order to reproduce this problem, I had to do dist. So I think it dies when running rust doc or something, which is always a good sign.
Yeah, I've definitely run into that.
Rust doc does some unusual things with the trait solver, which exercise some different paths. So I'm not that surprised. Right, so we've got some, I think what I would like to do is let's dump some state while we're here too. This is gonna generate a bunch of crap, isn't it? I hope not. Let's find out. I had some fun cases of like 2 terabyte log files while debugging the SYN thing.
Yeah, I always do my best to like get an MCB and then
it really makes life better.
Yeah.
The nice trick that I was using with some success, but that is a little risky, is like piping it through ripgrep-c 1000 or something. So you find some string that you care about, and then you get 1,000 lines before and after that string each time it appears. But then you never quite know, like, when you try to find every occurrence of something, or if it's not that exact string, you don't quite know if it's in there or not.
Yeah, I think it depends. Usually I can get an MCBE and then I just like log trait selection, infer, rusty middle, just the big traits.
Let's take a look here. So we're getting this hit from evaluate trait predicate recite recursively, which probably is here, right? That would be my guess. Like it's probably a provisional cache hit. And so what I'm wondering is, could it happen? I feel like there's something. Okay, maybe I can see how this, no, it feels like this shouldn't happen. This feels bad. So what I'm imagining could have happened is, I think I know what could happen. Maybe this is an argument for switching to DFNs, which isn't that much work. I think what could be happening is, let's try to sketch it out. Stop. Why are you doing that? I don't understand what it's doing. Don't make a new terminal. No. Eh.
I don't know. Maybe try closing the terminal.
Let's close something. Oh, I guess all that stuff was, that's fine. It doesn't matter. There we go. No. Why are you doing this to me? Also, how big is kill me? Pretty big. Okay. It's not worth it. We'll figure something else out. You know what we'll do is this.
You could just winnow it to the trait select module.
Yeah, that might help too. But also I should close this maybe. Something gonna let me have, I think I just have to restart VS Code. It's very grumpy. We'll worry about you later. So here's what I think is happening, even though I can't type to show you. I think that we are completing a provisional cache, and then the thing that which was dependent on, let's say, something with one depth, and then we go to do other things within that, which wind up making the depth higher, but we're not updating the cache entries, if that makes sense.
Yeah, I think that makes sense.
If we use DFN,
I think it would be the same problem.
and that's
right?
probably why I made one. That's probably why I had, yeah, that's why I had one depth in the beginning, because exactly this transitive thing, I didn't want to deal with it. I remember that now. It's good. We should probably add a test for this.
Yeah, good
It
luck.
is not like, yeah, I know exactly.
Good luck minimizing it.
It's some very sensitive. It's possible we could add a test for this. It
I'm
doesn't seem that hard.
surprised you were able to figure this out.
We should be able to make a test for this. Come on. Hold on. The problem with these tests is they're always so dependent on, like, I don't know. I mean, it's something like trait A. Well, I guess these have to be auto traits. Okay, it's something like struct A. Wait, hold on. Let's show the graph we want. The graph we want is A depends on B, depends on C, or maybe just B depends on B. And then B also depends on A. And then that will make B have a, or we probably need an intermediate node to make it really do the right thing. So this would have a depth of 1. This would have a depth of 0. And now the overall result is a depth of 0, right? What we can do, I actually I don't particularly love the structure of this cache because it's a hash map, which is annoying because so much of what we want to do is dependent on the depth first numbers, really. But like what we could very easily do is when we decide, when we're done with B and we see that we're going to insert our thing as provisional, we can also sweep everything with a higher depth first number that's in the cache and update its its reach depth should be the minimum of our reach depth, if that makes sense. You know,
Yeah.
I'm trying to think if that's early enough or if we can have a problem where you haven't yet left B and it's already annoying that it's out of date. I don't think so because basically the reach depth of everything that's in the cache is always something that is still on the stack. Like, in order to have a problem, it would have to be a depth of some node that was popped, right? That's the problem we're having, that we popped B from the stack. Like we didn't complete the whole assertion fails when we then go to process D and we find a provisional cache result for C with depth 1. This actually won't trigger the assertion, but if you make the thing a little more convoluted, it should. Like you need like another layer or something to make it depth 2, which is annoying. But that's where we have the problem. And the problem is that it's referring to B, but B was popped. But we maintain the invariant. If what we do is when we pop B and we see that B isn't ready yet, we go and update everybody's depth to B's depth, it must be something lower than B, or else B would have been ready. And so we kind of maintain that invariant that the depth is always referring to some parent on the stack, which might be ourselves, or which will never be, it will never be D, because D, if there's some common ancestor and D is a child of that, and at that point before D was pushed, everything on the stack referred to A or above. That makes sense. It does. It's true. Believe, trust me.
Trust me.
It's fine.
It sounds correct.
You can sort of see what I'm getting for, I hope.
Yeah.
Yeah, okay. So now I just have, that's the easiest fix, is to do that, but I would like to have a test. It's going to be annoying to make one though. I need the cache result to be depth 2. Oh, well, okay. So C has depth 1. So if A just depends on C, would that do it? I think that would do it. Because what would happen is A will come along, A will find the provisional cache result. C won't yet be on the stack.
Mhm.
So let's try it. I think this will work.
That looks right. Because it would go through B, update A with a depth of 0, go to C, see its depth 1, try to update A.
Need some garbage in the way to prevent it from, prevent other things from freaking out. C has to depend on B. Or let's just do like, no, that'll work. Of course, that worked fine.
But you don't depend on C again from A, right?
Oh,
It's only through.
good point.
Oh.
Still not good enough. Why? B depends on C and A. I don't know. Let's look at the logs. Why is it so smart? It could be that it's not even evaluating this. It might not even be going down this path, actually. It's kind of annoying. It's hard to make it. It's not always easy to make it do an evaluation.
Yeah, that's at least with chalk, right? You can just tell it what you want it to do.
Right. Trying to think what's a way to force it to do an evaluation. It will do it if there's two options that might apply. And it needs to narrow it down. So like we could do implement for all t my trait. No, for all t that are a, my trait for t, and implement my trait for unit.
I'm not sure that'll work because T implements A doesn't make sense. A is a struct.
Oh, you're right. That does not work. Send is what I wanted. But of course, that doesn't work. Well, I don't know.
I mean, I don't know. You could restrict T to, I don't know.
It's not going to work because it's not going to unify. What happens if I do this? No. Okay, I don't know. Just fix it, Amber.
Stop being so smart.
Stop being smart. All right, we'll try to just fix the bug. What we really need is, yeah. So insert
mean-
provisional.
I feel like when you update the DFN or the reach depth, that should just, if it's greater, just ignore it, right? Because
Well, that doesn't feel right to me because it actually does depend on, like, if C depends on A, like to go back to our example, I thought about that, but I think that's wrong because C really does depend on A here, right? And if we just ignored the depth, we don't know that. We don't realize that there's actually a dependency between processing C and the thing at depth 0. And so we might incorrectly assume that some parent node is complete.
wait, I'm confused. So we're at the point that we finish processing B. So the reach depth of A is going to be 0. We go to try to process C. Now we see that that's a reach depth of 1. We want to update A to be at least older
1.
than 1, but
Right,
it's
which it
already
is.
0.
Right, this doesn't show the
So-
problem. The problem would be if we suppose that we add some more layers in here. Don't make me write all the layers out. Suppose that we had another layer. I guess the layers have to be here. I hate this. Suppose that this was depth 1. Right? Now we'll get a reach depth of 2. Right? And we would go up, and this has reached depth 1 because it started that way. And this has reached depth 0. Now my concern is we walk up the stack, we say, well, that's inside of us. So we don't have to update our reach depth of 1.
Gotcha.
And then, but the problem is now we might actually cache this result in the global cache, when in fact, it does depend on A because C depends on B, which depends on A. So it's actually wrong.
Yeah, I see.
I think the right result, I'm trying to decide the most, I think that there's a number of times you could do this. But the
I mean,
bottom line is you have to, like, what we could do is, we could do the, what do you call it? Union find algorithm. Like, union find is probably actually the easiest way to do this, which is to say that we say, okay, wait, what was the minimum DFN? If we use DFNs and stuff, we could poke back up and get union find. That would be like that maximally efficient. We would just never forget though as the end result. We'd have the DFN for C would be, okay, well, C depended on B, and then we would unify B with A, and then we would say, we found C, let's refresh to whatever's the transient thing. Does that make sense?
yeah.
But I
Wait,
don't feel
so
like
hold
using
on.
union find.
Why
So,
did B not get updated to 0 here? Oh,
it will. B will get updated to 0, but that's not the problem. The problem is here, this is reach depth equals 1, because at the time when B gets,
but I mean, oh, I see what you mean. Yeah, because C depends on B, depends on A.
right. So the union find would be like the laziest thing, but I think just eagerly updating them when we pop B is the easier thing. And
Yeah.
probably more correct, or I don't know whether it's more efficient. They're probably both fine. That's what I'm gonna do. It's not hard, it's just annoying. Basically, I think what you would do is when you insert a provisional entry, you want to say everything with a DFN greater than my DFN has to have the minimum of its depth and my depth, because that's stuff that was added after I started, and it's all now dependent on anything that I'm dependent on.
Yeah. That sounds like it'll work.
It will work, and I do have to drop off now because I have another call. But we've at least, I think we covered everything. I wish I had a test for this. It's so annoying. We should add some Rust-C attribute or something that lets us
Be clever and tell Rusty
that
what to
lets
do.
us do like what we can do in Chalk.
Yeah.
Rust-C evaluate predicate a my trait or something.
Yeah.
The annoying thing is I could not convince that standalone test to reproduce for me in any way, partially because I don't have this. Like if I had this capability, I think we could do it.
Yeah.
But I couldn't like trigger the evaluates in the right order without turning off debug assertions and turning on other things.
Yeah.
No.
I mean, conceptually, I understand what's going on. I will have to go back and like look through your exact changes and like double check that everything lines up.
Yeah, no, it's good. I mean, it was good for me to talk it out in gruesome depth. I didn't encounter any points where I was like, oh, wait a minute. So that's a good sign. All right. See you later.
All right. Thanks. Bye.